And today we are going to discuss about the histograms. And a histogram is a measure of a frequency distribution. Okay? We have learned about the frequency distribution in the previous class. And this is the steps to construct a histogram with the equal bin width. So firstly, we need to label the bin boundaries on the horizontal line. This is the first step, okay, to construct the histogram. And secondly, we need to mark and label the vertical scale with frequencies or the relative frequencies. And what is the relative frequency? That is the ratio of the frequency and the total number of observations, right? So that is the frequency. And after that, above each bin, we need to draw a rectangle where height is equal to the frequency or the relative frequency corresponding to the bin. So these are the steps of the construction of the histogram with the equal bin width. So this is the example of the histogram about the previous table 6-4. And as you can see here, the x-axis indicates the compressive strength. Okay? The compressive strength of 80 alloy specimens, and the y-axis indicates the frequency or the relative frequency. So if we review the previous class, we need to first calculate the range, okay? Range of the observations. So the range was equal to the maximum value minus the minimum value, right? Right? So the maximum value was 245 and the minimum value was 76. Okay? Please see your previous slide. So the range was equal to 169. Okay? This is the range. And then we need to calculate the number of bins, right? Number of bins. And that is equal to the root n. And it's the total number of observations. Okay? So in this class, we have 80 alloy specimens, which means that this is equal to root 80. And that is equal to 8.9. Okay? And then we need to determine the class or bin width. And how can we calculate the bin width? That is the ratio of the range and the number of bins, right? So that is equal to 169 over 8.9. That is equal to 18.9. So this is the consideration from the experiment. So from these considerations, we need to decide first the number of bins, right? And the number of bins should be the integer value, right? So we can determine 9. Why? 9 is very close to the calculated number of bins here. Okay? And also, we can determine the bin width as 20. And this determination is based on this previous calculation. Okay? And it is dependent on the person who solved this example. Okay? And then we need to finally determine the starting point. the minimum value was 76 here, and the bin width was 20. So we can simply assume that the starting point is equal to 17. Okay? So this is the decision from these considerations. And from this data, this information, we can draw this histogram. For example, the starting point of the compressive strength is 70 here. Okay? And the width of bin is 20. Okay? This was determined based on this calculation. Okay? And also, the number of bins here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So, from this calculation, this process, we can determine the number of bins and the width of bins here. And based on this determination, we can calculate the frequency, right? The frequency is the number of samples included in each bin, right? And also, based on this frequency and the number of test samples, we also can calculate the relative frequency, okay? So, from this process, we can calculate this histogram. And as you can see here, this histogram has a very nice shape, and the shape of this distribution is very close to the distribution of the normal distribution, okay? The horizontal scale is the bin width, right? This is the bin width. And with label, this is the label. This is the compressive strength. And with the unit. Unit is the pound per square inch. And also, the vertical scale here is the measured, right? Measured frequency or the relative frequency, labels. Labels are here, frequency and the relative frequency. So, from this process, we can draw the histogram based on the observed data point. And now, we are going to discuss about the effect of number of bins on the histogram. Since the following figure here, this is the figure 6-8, has too many bins. The number of bins is equal to 17. The histogram is dramatically changed according to the x-axis, that is the strength. So, this histogram is based on the identical data point with the previous case, okay? But the only difference is that the number of bins is different, okay? So the previous case, we have 9 bins. And in this case, we have 17 bins, okay? The same. And as you can see here, the starting point is 70, okay? Identical with the previous case. And for this case, the starting point is equal to 17 pounds per square inch. This is the identical value with the previous case, okay? And the bin width was determined as 10, okay? So, the final value here will be 240, right? Because we have 17 bins, so 17 multiplied by 10 plus 70. That is the final value, okay? Right? So starting point is 70, and we have 17 bins with bin width 10. That is equal to 70 plus 170. That is equal to 240. Okay? So, from this process, we can have this histogram. Okay? And as you can see here, there are several bins with the identical frequency. Okay? These are the identical frequency. And also, these are the bins with the identical frequency. And identical frequency is dramatically changed at some point right here. And from this histogram, it is very difficult to determine the distribution of the frequency of the tested sample, which means that this is bad histogram. Okay? But in contrast, this figure figure 6-9 shows much gradual change, as you can see. No, the identical. And so this figure shows much gradual change and the better shape, which means that the shape of the distribution is close to the shape of the normal distribution. Then the previous figure 6-8, because of the appropriate number of bins selected, that is the 9. Okay? So from this comparison, we can draw a conclusion that from this process, we can first determine the appropriate number of bins, right? And also the appropriate bin width. So by using this process, we can always have this kind of better histogram as compared to the other ones. Okay? So for this case, so it is dependent on the person who solved this example. Okay? We can simply determine, okay, we're gonna have the 17 bins to show this data point by using the histogram. Right? But in this case, we have kind of bad histogram. Okay? So if we want to use the histogram, we need to calculate these things first. Okay? And based on this information, you need to draw the histogram. Okay? This is the process. 그러니까 히스토그램 데이터가 그냥 있고 제가 히스토그램을 그릴 수가 있어요. 그죠? 그럼 빈 숫자나 빈 폭 다 결정이 될 수가 있잖아요. 그러니까 이렇게 아무런 근거 없이 분포 자체가 이상하게 나옵니다. 이거를 히스토그램을 그리는 목적 자체가 이 디스트리뷰션을 잘 표현해주기 위해서인데 시각적으로 이렇게 그려주면 아무 의미가 없어요. 히스토그램을 그리는 의미가. 그죠? 그래서 이렇게 디스트리뷰션을 잘 표현해줄 수 있는 히스토그램을 그리기 위해서는 이 과정을 반드시 거쳐야 된다는 얘기예요. 아시겠죠? 그래서 이런 히스토그램을 얻을 수 있다는 얘기입니다. 아시겠죠? So, this is about the effect of number of bins on histograms. And also, I'm going to explain about the cumulative frequency plot. A cumulative histogram is useful in the data interpretation. For example, it is easily found that approximately 70% observations are less than or equal to 200 pounds per square inch strength based on this cumulative histogram. Okay? And this is the cumulative. Okay? The data point is identical, but this cumulative histogram. Okay? The Y frequency. From this histogram, we can easily find out the information that the 70%, okay, of the tested samples have the compressive strength less than or equal to 200 pounds per square inch. Okay? So this kind of data interpretation can be done by using this cumulative histogram effectively. Okay? So it depends on the engineer. If the engineer should have this kind of data analysis, they can simply draw the cumulative histogram and then they can determine. They can draw the decision. Okay? So this is about the cumulative histogram. And now we are going to discuss about the shape of a histogram. Okay? X tilde, this is the median, and X bar is the mean. Okay? X tilde and X bar are denoted as median. Median is called 중간값 in Korean. And also mean, that is called 평균 in Korean. We can say mean is also the average value. Okay? So X tilde denotes the median and X bar denotes the mean values. If the data is symmetric, okay, the median and mean values are identical. But if the data is symmetric, which means that data is skewed to the right or left, the median and mean values are not identical anymore. Okay? For example, this is the example. If 9 people obtain the following scores, what are the mean and median? Okay, that is the question. And this is the score from the 9 people. 4, 5, 6, 7, 8, 9. Okay? So for this case, this is the example. If 9 people obtain the following score here, okay? In this case, what are the mean and median? First, we are going to calculate the mean. This is the sample mean, right? So mean is equal to x bar. X bar is equal to the summation of all this score, right? 4 plus 4 plus 4 plus 5 plus blah 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 plus 9 over the number of data point that is equal to 9. Okay? And this is equal to, this is the 52 and this is the 9, that is equal to 5.78. This is the mean, okay? This is the sample mean. And what about the median in this case? Median is closely related to the location of the data point. And also, if we provide a data point in the ascending order, which means that this is the smallest data point and this is the largest data point, the fifth data point is the median, right? 중간값. So the median is equal to 5 in this case, right? And for this case, we are going to draw the histogram, okay? The x-axis indicates the score, and the y-axis indicates the frequency, okay? Frequency. And the score is from 4 to 9, so we can say this is the 4. 5, 6, 7, 8, 9, okay? And we have frequencies from 1, 2, and 3. So this is 1, this is 2, this is 3. So for the case of score 4, we have this rectangle, right? In the case of the score 5, we have this rectangle, right? Can you see? And for the case of the score from 6 to 9, we have this rectangle, right? Okay? And this is right skewed, which means that this is not a symmetric data point, right? And this is asymmetric data point. And in this case, if we have a larger value in your left side, we can say this is the right skewed distribution, okay? I'm going to say again, if you have a larger frequency values in the left side, this kind of distribution is called right skew distribution. And for example, if you have a larger frequency values in the right side, that is the left skew distribution. Okay? And for this case, this is the median, right? X tilde, and this is the mean X bar, right? X bar is equal to 5.78 here. So X bar is here, okay? And X tilde, this is the median. Median is here. And from this case, X bar is larger than X tilde, okay? Right? So if you calculate the median and mean, and if the mean value is larger than the X tilde, we can say this is the right skew distribution. Okay? And if you obtained the X tilde, the median, is larger than the mean X bar, that will be the left skew distribution. And this is the example. The B is the symmetric case. Okay? And then this is the identical value. And of the C, the right skew distribution, X bar, the mean is always larger than the X tilde median. Okay? And we can say this is the positive distribution. And if the X tilde, which is the median, is always larger than the mean, X bar, this is called the left skew distribution. And also we can say this is the negative distribution. Okay? And this histogram can be calculated based on these kind of examples. Okay? So this is the right skew distribution, and we can verify that the mean is always larger than the median, X tilde. Okay? So this is about the shape of a histogram. And now we are going to discuss about the box plot. And what is the box plot? The box plot is a graphical display that simultaneously describes several important features of a data set, such as center, this will be median, okay, and spread, okay, and also the departure from symmetric, etc. Departure from symmetric is that 대칭으로부터 얼마큼 이제 편차가 있는지를 판단할 수가 있어요, 박스 플러스로부터. And it displays the 5 important points. The first one is the minimum value. The second one is the first quartile, okay, Q1. And the third one is the second quartile, or this is the median, okay. And the first one is the Q3, this is the third quartile. And the last one is the maximum value. So the box plot includes these 5 important points. And this is the schematic description of a box plot. And this is the first quartile here. And this is the second quartile. And this is the third quartile. And based on these 3 lines, we can fabricate this box first. Okay? And then we need to provide this range from the first quartile. Okay? And that is 1.5 times the interquartile range. What is the interquartile range? That is Q3 minus Q1. Okay? Right? Please see your previous slide. And we know about the interquartile range because we know about the first quartile, second quartile, and third quartile. And so we can calculate the 1.5 times interquartile range. And if we calculate this range, we can find out the smallest data point within the 1.5 interquartile ranges from the first quartile. Okay? We have more data point here. But the data point beyond this line, 1.5 interquartile range from the first quartile, we are going to neglect those data points. Okay? So the smallest data point in this box plot will be the smallest data point within the 1.5 interquartile ranges from the first quartile. Okay? So this is the smallest data point, okay, included in this 1.5 times interquartile range. Okay? And we have more data point here beyond this range, but we are not going to discuss about this point. Okay? We are going to neglect. Okay? And also, we can have the same range to the maximum side, which means that this is also 1.5 times the interquartile range, okay, from the third quartile here. And this is the largest data point within 1.5 interquartile ranges from the third quartile. Okay? So, based on this largest data point, we can draw this line. Okay? And beyond this 1.5 times interquartile range, right here, and we normally provide this information by just that. Okay? So, this is the schematic description of the box plot. Okay? So this can be well understood based on this, the next slide. Okay? And this is about the box plot for the compressive strength data. We already obtained the compressive strength data of 80 alloy specimens, right? Right? In the previous table 6-2, we already obtained the compressive strength data of the 80 alloy specimens. And based on that data, we can draw this kind of box plot. Okay? And we can determine the second quartile, that is 161.5. And also, we can draw this first quartile and the third quartile. And also, we can determine the smallest value within the range of 1.5 times interquartile range. And also, this is the largest value within the range of 1.5 times interquartile range, okay, from the third quartile line. So we can draw this box plot first, okay? And as I mentioned previously, we can provide the dots for the data beyond the range of 1.5 times interquartile range. Okay? So, based on the concept of the box plot, we can draw this diagram. And the reason why we normally provide this diagram can be explained in this sentence. That is, the box plot indicates the distribution of the compressive strength is fairly symmetric around the center line because the length of whiskers and the top and bottom boxes are quite similar. And in other words, this is the median value, right? And the width of the top and bottom box are quite similar. Okay? Okay? And dependent on the data point you obtained, the width of these two boxes can be changed. Based on the previous box plot, as you can see here, the width of these two boxes are different. But in this case, the width of these two boxes are quite similar. And also, the length of whiskers here are quite similar as well. And this means that the data of the compressive strength data of the 80 alloy specimens are well distributed. Okay? And this is quite symmetric distribution. Okay? So from the previous histogram, we can determine the shape of the distribution of the data, right? So we can determine the data point is symmetric or asymmetric. Okay? And from this box plot, we also can determine the distribution of the data point. Okay? Because we know about the center line, and we know about the first quartile and the third quartile, and this kind of smallest and largest data point, we can easily determine the distribution of the data point. Okay? And we can say, from this box plot, we can say the data point from the 80 alloy specimens are quite symmetric. Okay? So this is another tool to visually display about the distribution of the data point, okay? Like the histogram. And this is about the comparative box plot. And this is the comparative box plot of a quality index at 3 manufacturing plants. And this is the manufacturing plant number 1, and this is the manufacturing plant number 2, and this is the manufacturing plant number 3. And from this figure, the figure 6-15 reveals that there is too much variability at the manufacturing plant 2 as compared to those of manufacturing plant 1 and manufacturing plant 3. Why? Because the distance between the maximum and smallest value is highest for this case, right? So we can say the scatterness of the data point obtained from the manufacturing plant 2 is largest. Okay? Okay? So the product manufactured from the manufacturing plant 2 has the largest variability. Okay? As compared to those from the manufacturing plant 3 and the manufacturing plant 1. Okay? So by using this comparative box plot, we can determine the variability of the data point. Okay? According to the samples. And also, the manufacturing plant 2 and 3 need to raise their quality index performance as compared to that of manufacturing plant 1. Why? Because the manufacturing plant 1 has the highest median quality index as compared to those of the manufacturing plant 2 and manufacturing plant 3, right? So from this box plot, we can simply determine that the manufacturing plant 2 and plant 3 should increase their quality index performance as compared to that of the manufacturing plant 1. Okay? So from this box plot, we can interpret the data effectively. Okay? The scatterness of the data point and also the median value of the data point. So this is the reason why we sometimes use the box plot instead of the histogram. Okay? Okay. And now we are going to discuss about the time sequence plots. A time sequence plot is a graph in which the vertical axis denotes the observed value of the variable, and the horizontal axis denotes the time, which could be minutes, dates, years, or etc. So it is called a time sequence plot. So the following figure 6-16.8 here shows that the sales, this is the y-axis, sales increase continuously with the year. Okay? As you can see here, this is the year, okay, time axis, and this is the y-axis is the sale, and sale continuously increases with the year. Okay? But figure 6-16b here shows that the sales exhibit a cyclic variability by quarter, regardless of the year, which means that this kind of cycle change of the sale is obtained. And regardless of the year, the first and second quarters always have the higher value than those of the third and fourth quarter here, right? So from this time sequence plot, we can determine the change of the data point according to the time, okay? And this is about the digidot plot. And what is the digital plot? J.S. Hunter in 1988 suggested combining the stem and leaf diagram with a time sequence plot to form a digital plot. We already have learned about the stem and leaf diagram, right? And we discussed about the time sequence plot in the previous slide. And the digital plot is the combination of the stem and leaf diagram with a time sequence plot, okay? The digital plot effectively displays the overall variability in the compressive strength data and also simultaneously shows the variability in this measurement over time. So, in the case of stem and leaf diagram, we can easily see the distribution of the data point, okay? Do you remember that, right? So, the purpose of using the stem and leaf diagram is to see the distribution of the data point, right, according to the variable. And the purpose of using the time sequence plot is to see the change of the data according to the time. Sometimes we need those two information, right? So in that case, we can effectively use this digital plot, okay? And so this is the example of the digital plot of the compressive strength data in the previous table 6/2 about the 80 alloy specimens. And we can first draw these two columns, okay? This is the stem and leaf diagram, right? The minimum value is 76, okay? And the maximum value is 245. So we first can draw this stem and leaf, and then to the beside the stem and leaf diagram, we can draw this time sequence plot, which means that the x-axis should be the time, and the y-axis should be the compressive strength. So, I'm going to let you know how to fabricate the digital plot here. This is the time, okay? And this is the compressive strength. Okay? And this is for the time sequence plot. And also, we can draw this stem and leaf diagram here, okay? The minimum value was 76, and the maximum value was 245, okay? We can draw all the data points here, right? So, this is 7, 8. This is the 97, and this is the 1, 5, 10, blah, blah, blah. And we can first draw this figure, and this is the smallest value, right? And we can say this is the 76, okay, in this diagram. And this is the maximum value. This is the 145. And for this case, we need to assume that this y has identical interval. Okay? And then we can draw the data point according to the time. Okay? And if we obtain the data point, here first, and here, and here, And we can draw this time sequence plot, okay? Because we obtain the data with the time. And we can simply display the data point with the time, okay? This is a time sequence plot. But for this case, if we draw the stem and leaf diagram beside the time sequence plot, we need to make sure that the minimum point and the maximum point is identical. Here, here, okay? And then we can assume that this is, the y-axis has the identical interval. And in this case, the stem is continuous, right? So, for example, this is the 97 pound per square inch compressive strength, okay? We obtained from the data point, from the experiment. And as you can see, this point in this time sequence plot is very similar to the data point in the stem and leaf diagram. Okay? Okay? So, from this stem and leaf diagram, we first can simply know the distribution of the data point here, right? And we can simply draw a conclusion that the alloy specimens has the compressive strength between 100 to 200, okay? Because there are the most data points here. And also, the change of the data point with the time can be seen from this time sequence plot, okay? So from this digital plot, we can obtain informations. First one is the distribution of the data point, and also the variability of the data point with the time, okay, simultaneously. So this is about the d-dot plot, and sometimes it is very effective, okay, to interpret the data. And now we are going to discuss about the probability plots. And this is a question: how do we know if a particular probability distribution is reasonable model for the data set we obtained? Right? We need to determine the selected probability distribution model is appropriate to the data point we obtained. Then we can analyze and we can interpret the data point, right? And this is the definition of the probability plot. A probability plot is a graphical method for determining whether the sample data obtained conform to the hypothesized distribution based on a subjective visual examination of the data. And which means that we can determine the probability distribution based on the obtained data by using histogram or box plot, etc. Right? And if we want to use that kind of probability distribution, we need to draw a conclusion that this hypothesized distribution is well correlated with the data point we obtained. Right? So how can we determine those kind of things? We can use this probability plot. Okay? So the reason why we have to use the probability plot is to determine whether the hypothesized distribution is can be used to analyze the obtained sample data point. Okay? So to construct this probability plot, we need to following the steps. This is the first one. We need to sort the data observed from the smallest to the largest, which means that we need to provide a data point in the ascending order. Okay? 그러니까 증가하게끔 놔야 돼요. 처음에 가장 작은 걸 놓고 그 다음에 가장 큰 게 나중에 오게끔. So first step is that we need to sort the data observed from the smallest to the largest. So this means that the x1 is the smallest value, okay? And xn is the largest value. And secondly, the observed value, xj, is plotted against their observed cumulative frequency. The cumulative frequency is defined by the following equation, j minus 0.5 over n. And n is the total number of data points, okay? And j is the number of data points from the smallest data point to the data point xj, okay? Okay? So this equation is the cumulative frequency. This is the second step. We need to calculate the cumulative frequency. And the last step is that if the plotted points form a straight line, it is reasonable to say that the hypothesized distribution adequately describes the data. Okay? So this is the steps to construct a probability plot. And you can easily understand the probability plot from this example. This is the example 6-7 about the battery life. 10 observations on the effective service life in minutes of batteries used in a portable personal computer are as follows. 176, 191, and 214, blah, 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 and 185. In this case, the smallest value is 176 here, and the largest value is the 220. And we have 10 observations, okay? And for this case, we hypothesize that the battery life is adequately modeled by a normal distribution. That is the assumption, okay? Then we now first arrange the observations in ascending order. This is the first step to construct the probability plot and calculate their cumulative frequencies, j minus 0.5 over n. And this calculation is summarized in the following table, 6-6 here. So this column indicates the j. J is from 1 to 10, right? Because we have 10 specimens, 10 observations. And this is the xj. And xj is given in the ascending order. And this is the smallest value, and this is the largest value. And we can calculate this cumulative frequency, right? J minus 0.5 over n. N is equal to 10. Okay? So in the case of j, when j is equal to 1, 1 minus 0.1 is equal to 0.1 over 10 is equal to 0.05. Okay? And in the case of 2, 2 minus 0.1 is equal to 1.5. 1.5 over 10 is equal to 0.15. Right? So we can calculate all these things from the same procedure. And Zj will be discussed in the later slide. Okay? So from this information, we can draw this curve. The x-axis indicates xj. This is the observation. And also, the y-axis indicates the cumulative frequency. But to change this value to the percentage, we multiply 100 here. Okay? This is the cumulative frequency. And we multiply 100 here to have the percentage. Okay? And this dot indicates the observed data from this table. And this is the straight line to evaluate its stability subjectively. Okay? And the data, observed data, is well simulated with the normal probability. Right? Why? Because the observed data exhibit similar behavior with this straight line. Okay? So we can determine that the observed data point is well simulated based on the normal probability distribution. Okay? So this is about the probability plot. Okay? And this is about the probability plot on ordinary axis. A normal probability plot can also be constructed on ordinary axis by plotting the standardized normal score, Zj, against Xj as follows. This is the cumulative frequency, right? Z minus 0.5 over n. And if we provide this equation, this is equal to the probability of Z. Z is the standard normalized random variable, right? And this value should be lower than or equal to Zj. And we can calculate this value very easily, right? And we can, since this is the standard normal distribution, we can use the appendix table. Then we can simply obtain the Zj. Okay? So, for example, if j is equal to 1, the j minus 0.5 over n will be 0.5 over 10, that is equal to 0.05, right? When j is equal to 1, okay? And this should be equal to the probability of z, which is the standard normal random variable. And this should be smaller than or equal to small zj. And if you see your appendix table, we can easily find that Zj is equal to minus 1.64. Okay? And as you can see here, when x first, x1 here, the Zj is equal to minus 1.64. And if j is equal to 10, this is equal to 0.9, right? Because 10 minus 0.5 over 10, that is equal to 0.95. And also, if we use the appendix table, the Zj is equal to 1.65. Okay? So, x10 here, Zj is very close to the value of 1.65. Okay? So, from this equation, we can change the cumulative frequency to this standardized normal score Zj for the case of the normal probability plot. Okay? So, if the data point is following the normal distribution, we can simply change this cumulative frequency to this standardized normal score. And based on this case, we can determine the shapes of the probability distribution. The probability plot can identify various shapes of the probability distribution. And lighter tails of the distribution indicate severe peak. And heavier tails of the distribution indicate smaller peak. And this will be discussed in the next slide. And we can also have the skewed distribution. And I'm going to let you know how we can evaluate those kind of things. The various shapes of the probability distribution can be seen in the next figure, 6-21 here. And this is the normal probability plot indicating a non-normal distribution. Okay? A, this case indicates right-tailed distribution. And B, this case indicates the heavy-tailed distribution. And C indicates right-skewed distribution. For the light tail distribution, this case, the observations on the left side here, this is the observations, are below the line, okay? Okay. Whereas those on the right side here, the data point, the observations are above the line, okay? And for this case, we can say this is the light-tailed distribution. And I'm going to show about this case. This is the variable x, and this is the probability density function. For this case, this is the normal distribution, okay? And for the case of the light-tailed distribution, light-tailed means that the lower value at the tail is obtained, okay? So this is the case of so as compared to the normal distribution, we have a higher point at the center, okay? Higher probability at the center, but we have lower probability at the tail. We can say this is the light-tailed distribution, okay? And if we analyze this curve based on the probability plot, we can have this kind of shape. The left points are below, the left observations are below the straight line, and the right observations are above the straight line, okay? And the second one is the heavy-tailed distribution. In this case, the observations on the left side here is above the line, whereas those on the right side here are below the line. This is exactly reverse to the previous light-tail distribution. And for this case, this is the x, and this is the probability density function. And we have this kind of normal distribution, okay? This is the normal distribution. And for the case of the heavy-tailed distribution, we have a higher probability at the tail, okay? So in the case of the heavy-tailed distribution, we have a higher probability at the tail, but instead we have a smaller probability at the center as compared to the normal distribution, okay? And for this case, if we analyze this curve based on the probability plot, we graph, okay? The left observations are above the center line, the right observations are below the center line. And the last one is that the right skew distribution. The observations on both sides will be below the line. As you can see here, both the left and right observations are below the center line. And for this case, this is the right skew distribution. And what is the right skew distribution? And we can say this is the normal distribution. If we have this kind of data distribution, okay, and we can say this is the right skew distribution, and if we analyze this curve based on the probability plot, we can have this kind of graph, okay? Left and right observation line. And what is the reverse case? If the both left and right observations are above the center line, we can have the left skew distribution, right? Okay. If the left and right observations are above the line, the straight line, we can have this kind of left skew distribution. Okay? So, from this probability plot, we can determine whether the selected probability distribution is appropriate to the obtained data point or not. Okay? So that is the purpose of using the this probability plot, okay, from this class.